Usually when we talk about design patterns within AI agents, we actually need to make this important distinction because there are two different types of categories of design patterns. Divided by topology, meaning the structure, for example, single agent pattern, sequential pattern, and so on, and by their capabilities, like react, plan, and execute. But most of the videos on YouTube and articles on the internet are not gonna make this distinction. So this is why if you wanna learn all about the design patterns in the right way and how these categories actually interact with each other, this is the right video for you, and it's going to be quite interesting, I promise. So the first one is going to be the single agent pattern. And I have to say that this is the one that you're going to use most of the time. Like 80% of the production AI agents are going to be using the single agent pattern. I'm going to tell you why. The single agent pattern is actually consisting only of one agent. Think about one single microservice. And this pattern plays well with the React pattern by capability. Now, React is reason and act, meaning you're using the same LLM. So let's say within this agent, we're generating a thought, right? We are making a call to a same LLM. Then we might store this call or thought rather. We might make a tool call if we need it, for example, to a database or scrape the web. And then the observation is also, again, calling the same LLM, right? It's calling the same LLM and thinking, hey, do we have enough information? If not, then we generate another thought. So it's kind of a small loop, right? If we do have enough information, then the agent simply gives the output. And this is gonna look like this. It's very simple. Actually, we have just one agent node and we have one condition. Should we continue or not? So the agent node makes this invoke and it passes the state with messages. Now, of course, this is simplified because we're assuming that the thought and the action is just one LLM call. And since it sees the history so far, it also knows the thoughts. So the answer might look something like this. So if you invoke the LLM, you're going to get some structured output, let's say. So you're going to have type text, and the text will be, the user wants today's weather in Sevilla. This is the thought. And I should call the weather tool with Sevilla's coordinates. And this is the action. As you can see, the thought and the action are literally merged together. And the should continue is kind of a coordination edge, which decides whether we should continue or not. And this is basically this part. Do we have enough information from the observation or not? And as I said, this matches perfectly the React design pattern and the tool use design pattern. And there are two more that are also going to come up. Now, the next one will be the sequential model. If you remember, I said that 80% of the production AI agents are using the single agent pattern. And if you look at this code, you can actually add as many nodes as you want and make your logic quite complex without needing to deploy another microservice or another AI agent within your infrastructure, right? You can handle it all within one AI agent. But sometimes we want to have this sequential model, all right? And this is the second one. The sequential pattern is where you have two distinct agent. One of them, let's say a planner, and one of them is an executor. And this fits perfectly the plan and execute pattern by capability. So if we go up, we're going to see that we have another guy here called plan and execute. And the role of this one is to separate planning, because we can plan with a more expensive model like Sonnet, and we're going to be paying more. But the actual execution, once we have this plan saved somewhere, is much cheaper. And we can do it with Haiku. Haiku doesn't have to think. It just doesn't have to reason. It just needs to execute. And execution will be done with a different model. Now, the question is, can this be done with the same agent? Let's say we just have one agent and we have two different nodes. So these are not going to be agents. These are just going to be node. Right? You can also call it a worker, whatever fits your vocabulary better. And the answer is yes. So if we look at the example of the sequential one, we're going to see that in this example, we are actually living within one single agent. Okay, so we have a plan node. And for this one, we're using a different Sonnet 4.6. And for the execution, we're using 4.5. And we have two different nodes. And what we do is also, of course, we have whether we should continue or not. And basically, you see that we're connecting these edges within one single agent. Now, the question is now, Why is it preferred to, first of all, separate the planning and execution? And this is the answer. Because it's much more cheaper. So we're going to saving a lot of costs because we don't have to do the execution with an expensive model. Second of all, it's much easier to debug, and predictability is easier because reasoning or planning is one thing and execution is one thing. It's modular, right? And it's very natural to put a human in the loop, right? Let's say we have a plan, and before the execution starts, you can add another conditional node here, let's say somewhere in between here, between this guy, and it's going to be a human in the loop where the human actually approves the action or execution, right? Okay, now to the second question. Should this live within the same agent, or should this be two different agents as we saw before? Now, I would suggest it should live, it actually depends on your architecture. So does your application really have complex, long contexts? If so, probably having two different agents and having agent-to-agent communication is better. But also keep in mind that this communication, so agent-to-agent protocol, and I actually have a video on this agent-to-agent protocol, this is going to cause some latency because sending data over the internet is not going to be cheap, right? In terms of time. Are these using two different tools? Like, is this agent using different tools than this one? If they're using the same one, maybe just keep them within the same agent. Do they have shared memory? Because if they have shared memory, this example already is enough. Also, do they have different validation paths? Like, does the output of this agent or agent/node is validated separately than this one? And do they have different permissions? Can you actually run them within the same process? If not, maybe just create another agent, right? Long story short, split them by accountability, not the job title. Don't look at the job title, right? Don't say, oh, this is an executor. Let's create another node or let's put another microservice. Think about the accountability. Now we're going to move to the third pattern, which is called parallel pattern. And in the parallel pattern, it's very common to use the orchestrator pattern, okay? Or plan execute can also be, but most of the time it's orchestrator because you would have one orchestrator that spins out two worker nodes like these guys and runs them in parallel. Let's say you're a travel agency, travel website, and when the user says, I want to travel to Spain, you spin two different sub-agents, let's say one for that's looking for car rentals, another one that's looking for hotels, and so on. You get the idea. So obviously we're going to be saving time here because these two agents are going to be working in parallel, but we're also going to be paying more costs. So cost multiplies with concurrent calls, and the latency is bounded by the slowest worker. Let's say this guy was slower, and the answer that is going to be given to the user is going to depend on the slowest worker. So it's only worth when subtasks are genuinely different in nature. Because if we're looking for car rentals here and hotels, we don't want to wait until the answer for the car rentals is retrieved and only then we can process the hotels. We can do them in parallel, right? These are two distinct actions. And this is why the orchestrator is fitting perfectly here. And I would say if 80% of these guys are usually the single agent, Orchestrator fits into a single agent architecture as well. So if you think about it, you can do the same thing within this single architecture as well. You can imagine that this is actually the same agent, right? So this is going to be the orchestrator node, and this is going to be the worker nodes, right? So if we look at the example here, we're going to see that we have one orchestrator state and we have subtasks and worker states. So this is the orchestrator node, and we give it kind of a task. We say break this into independent subtasks that can run concurrently, only split if subtasks don't depend on each other, as in the traveling example. So once we have those subtasks, we're just going to dispatch them, and this is how the graph looks like at the end. And then we didn't have it on the board, but you can also have an aggregate node, which simply aggregates the results from those different worker nodes and then just gives them to the user. Now, one thing I actually left out is the following: the coordinator pattern or the router pattern, also called. Now, what is this? It is pretty much the same as the orchestrator, but now the orchestrator is not an orchestrator, but it's more of a router, right? So the router is going to be a very cheap model, let's say Haiku, and these are actually the agent nodes or worker nodes that are connected to a more expensive LLM, right? So these are connected to Sonnet, okay? And this one too. And the router is simply going to decide where to route the request. Very similar to an API gateway, if you know how the APIs are designed. Now, what is the difference between this and the orchestrator? As I said, the router one is going to be using a cheaper model, but the orchestrator, if I undo this and we have the orchestrator here, usually the orchestrator is going to have also a very capable or an LLM that has reasoning, let's say Opus or Sonnet, right? And the orchestrator is usually going to be pulling the results from the worker and then deciding whether to dispatch another action or not. So the orchestrator is going to be kind of the brain. So these two patterns are also quite different. And most of the times, routing actually works better nowadays, I would say. So last one that we want to talk about is the loop pattern. Okay, so the loop pattern is kind of a new and emerging pattern, and it uses the reflection one. Okay, so the reflection by capability, and let's take a look at what it looks like. Kind of looks simple. So let's say one agent, right? You can also split them into different agents if you want. Again, you already know the trade-offs, but let's say we're living within the same agent, and within the same agent, we're going to have a generator worker and the evaluator worker or node. Again, very confusing vocabulary. I know I'm even mixing up the vocabulary myself, but at least you know that worker and node is kind of the same thing in this case. So this also fits the pattern called reflection or evaluator optimizer. Now, it's kind of similar to GANs, where we have one node which talks to one LLM, right? One LLM, and it can be the same LLM actually, and it generates kind of a code. This pattern is very much used for code generation, right? Let's say our code that we write in C++ or C# or Python or a SQL, or we need to validate the structure, right? You want your code to be very precise. If you miss the semicolon, then your code is not going to compile. So this pattern is perfect for code generation, or let's say compliance, where we have to be strict. So this pattern would be perfect when we have a clear and checkable success criteria. We know that our answer will be code, and we don't want any missing semicolons. We know that on the first try, it might be either common that we make a mistake or costly. That's why we want this iteration, okay? So we generate something, the evaluator evaluates. It says, it gives the structured feedback. If this is not good enough, we generate again, and the evaluator evaluates. So back and forth multiple times until the generated text or code usually is perfect. And then we can go ahead, right? Then we simply tell the brain or the agent then, hey, this is the output, and we give it to the user. Now let's take a look at the code. So the loop evaluator will be something like this. And this is pretty much a loop, right? Back and forth. Imagine it's a circle. So we're going to have a generator node, and we're going to have a critique node. So the generate is going to write a draft every time, and the critique one is going to evaluate the draft and pass only if it fully meets the criteria, okay? And then we give the feedback. And also we have this conditional edge where we say if passed, then we reach the max iteration, then we end. Otherwise, we generate, all right? This is quite simple, and this is also widely used nowadays for tasks such as code generation. All right, guys, if you learned something new, don't forget to give this channel or give this video a like. It's gonna help immensely, and also subscribe so that you don't miss any future videos. I'm gonna see you in the next one. Goodbye.